Good day and hello to everyone. This is the first of a series of videos which I'm going to present in order to explain how data is represented using computers. We will start with particularly the number systems that are used by computers, and we will go into a conversion process which will demonstrate how decimal numbers are converted into binary numbers and vice versa. So, what is a number system? In all aspects of we always use numbers, like to count certain items, to compute the change, and when you are riding a jeepney or buying groceries, and many other things. Inside computers also use number systems to represent quantities. And it is important to explain or to understand the nature of number systems in order to understand how they are used to represent data inside computers or in computer systems. A number system is a method used to represent quantities using symbols. In a number system, a single symbol is used to represent a unit and can represent limited quantities. When larger quantities need to be represented, we'll have to use a set of symbols, more symbols in order to represent bigger quantities, where each symbol represents a place value. A place value is a multiplier assigned to a location of a group of symbols to represent higher quantities. For example, in the decimal number system, the number 16 has the following place values. The symbol 6 has a place value of 1 or 10 to the 0, 10 to the 0 being 1. And the symbol 1 has a value of 10 or 10 to the 1. So the actual quantity represented is actually computed by adding 1 times 10 to the first power, which is 10, and added to 6 times 10 to the 0, which is 6. So 10 plus 6 is equal to 1, 6, or 16 in base 10. Different number systems have different sets of symbols and designated values. For example, the decimal number system uses the numbers 0 to 9, and the base of the place value is 10. When we say base, the place value is computed by ascending series of exponents starting with 0. In the binary system, for example, the values are 0 and 1, and the base used for computing the place value is 2. The hexadecimal system are values 0 to F, with A being 10, B, B being 11, and C being 12, and 15 correspondingly represented by F. So the base used for computing the place value is 16 or 116. Please note that the ascending powers of the base start with the exponent 0. So the basic unit is multiplied with the base raised to the exponent 0. Binary systems are used in computers, especially even in early computers like the IAS and EDVAC. Binary codes are used to represent non-numeric symbols like alphabets and numbers. The common binary codes were BCD, which was used in the for early IBM computers, and EBCDIC, or Extended Binary Coded Decimal Interchange Code. In modern computers, characters are represented using the ASCII or ASCII, which stands for American Standard Code for Information Interchange. In the binary number system, quantities are represented using bits, and binary numbers are used to represent large quantities using limited computer memory space. A bit is the smallest element of information. It is the basic unit of a binary number. It holds one of the two symbols, either 0 or 1. A nibble is the smallest set of bits. It's a set of 4 bits. it gives a maximum number of 16 possible different values. Now, in a set of binary numbers, we assign a bit as the least significant bit and another one as the most significant bit, or respectively LSB and MSB. The least significant bit is the bit with the smallest place value. And the most significant bit is the bit with the highest place value. In this diagram, for example, we have a nibble which represents a quantity of 1011 in binary. We usually count the bits from right to left, bit 0 being the least significant bit, and bit 3, which is the most significant bit. We say it's the most significant bit because it has the highest place value. Since it's bit 3, the place value is 2 to the third. So in this case, 1 is multiplied with a value of 2 to the third. Remember, 2 to the third is 8. So this is the place value. The symbol 0 represents a quantity of 2 squared, or 2 to the second power, which is 4. And the value 1 here, the second value 1, represents a value of uh, 2 to the first power. We just raise 2, the base 2, to the exponent indicated by the location or the position of the number. So this is 2 to the first power is 2. And the last bit being the least significant bit will have a base value of 2 to the 0, which is actually 1. So in this case, bit 3, the most significant bit, has a value of 8. Bit 2 being 0 has a value of 0. Bit 1 represents a quantity of 2 and bit 0 represents a quantity of 1. We add them together, 8 plus 4 plus 2, that's 11, which means that 1011 in binary is actually 11 in decimal. The second grouping of bytes is called, or rather bits, is called a byte. A byte is a group of 8 bits. Uh, this comprise this comprises actually two groups of nibbles uh, concatenated together or set together side by side. So in a byte, the least significant bit has a place value of 1, which is 2 to the 0, and the most significant bit has a place value of 128. So the place values are ascending exponents of 2, or the base 2. So in this example, the second place value is 2 to the 1, which is 2. The third place value is 4 because it is 2 squared. The next place value is 8 because it's 2 cubed, and 16, which is 2 to the fourth, and 32, which is 2 to the fifth, and 64 being 2 to the sixth, and 128 being 2 to the eighth. They can also be used to store numeric values, no? So particularly values 0 to 255. Or if you set aside 1 byte to represent a sign, it can represent quantities 127 to negative 128. What is an integer? An integer is a numeric representation that can actually be stored using the ASCII format. The more efficient way of storing information is to use a different coding scheme. The coding scheme is shown below, where we have, this is called the sign bit representation. So in a group of 2 bytes, in the sign bit representation, the 15th, or the supposedly most significant bit is set aside to signify the sign. The where the value of 1 represents a negative value or negative magnitude. The value of 0 represents a positive magnitude. And the numeric quantity is represented by bit 0 to bit 14. And remember that in an integer, no, only whole numbers can be stored. integers do not contain fractional parts. For example, the numbers below differentiate between uh, integers and non-integers. For example, 123 is a valid integer, 0.987 is not valid. 0 is a valid integer, but 0.0 is not. 78,903 is also a valid integer, but 123.09 is not an integer. The sign bit, which is the bit 15, indicates whether the number is positive or negative. Signed integers using 16 bits have a number range of negative 32,768 to positive 32,767. That's 2-byte integers. To store larger integer values would require more bits. Some systems and languages also support unsigned integers, which are deemed to be positive only. What are the relationships between decimal and binary integers? Actually, they can be used to represent the same sets of quantities. For example, in binary, rather in decimal, the number 13 is actually 1 times 10 to the first power plus 3 times 10 to the 0 power. So which means we have 1 times 10 plus 3, which is 13. In binary, the equivalent of 13 is 1102 base 2, where the first one represents a place value of 2 cubed. So that's 1 times 2 cubed. And the second one represents a value of 2 squared, or 4. And the 0 represents a value of 2, which is 2 to the first power. And the last one represents a value of 1, which is 2 to the 0 power. So in other words, we will have 1 plus 2, which is 3, plus 4, which is 7, and uh, no, we don't have a 2. We'll have 1 plus 4, which is 5. Okay. 1 plus 4 plus 8, which gives us a value of 13. So that's the same representation of the same quantities in the two numeric systems. To understand the representation of fractions in binary, we compare it to how it is represented in decimal. For example, in decimal, if you have the value 0.625, we're going to the right part of the decimal point. When you go to the left, you multiply it with an ascending exponent of the base. But going to the right, we divide it with an ascending exponent of the base. So therefore, in the value 0.625, zero point 0.6 represent a quantity of 1 divided by 2 to the 10. Rather, 6 times 10, 10 to the negative 1. Okay. So 10 to the negative 1. So this is 6 over 10. And 2 represents a quantity of 10 to the negative 2, or 2 divided by 100. And 5 represents a quantity of 10 to the negative 3, or 5 divided by 1000. So we have 0.625. In the binary equivalent, 0.101 is used to represent as 1 times 2 to the negative 1, or the first one being 1 half. 0 is 1/4, and the third digit is 1/8. 1 square, 1 half, 1/4, and 1/8. The succeeding will be 1 over 16. So in this case, the 0.625 equivalent of in binary is 0.101, because 1 half is 0.5 and 1/8 is 0.025. Okay. So decimal and binary are very much the same. When you go to the left of the binary or decimal point, the place values are an ascending series of the base. And when you go to the right, it's an ascending series also of the base, using it as a divisor this time, no? Not as a multiplier. So one way to represent uh, uh, fractional values is using fixed point numbers. What's a fixed point number? It is a number where the binary point is fixed at a given location. For example, in decimal, if you have 26.5, the decimal point is af after the digit 5 in the decimal value in the decimal system. The equivalent in the binary system is 1010.1, where point 1 is assigned a value of 1 half. So remember that 1 half is equal to 0.5 in decimal. And 26 is represented as 110101. So they are similar except that the base is using a place value of 2 instead of 10. So in this case, for example, the first one is 1, which is 2 to the fourth, which is 6. The second one is 1 is times 2 to the cube, which is 8. The next one, which is insignificant because it's 0. The third one is 2 squared. Okay, and the last one, which is insignificant, which is 0. So we will have 16 plus 8 plus 2 and plus 1 half, which is 0.5, which is thereby equivalent to 26.5. So on this example, if you represent this binary number, assuming that there's a decimal point at the third position, this is used to represent the following real number. Okay. 1 0 before the decimal point is 2, because this is the first place value is 1, the second place value is 2. On the other hand, the 110 has the following place values. The first one has a place value of 1 half, 0.5. The second one has a place value of 1/4, which is 0.25. The last digit, which is 0, supposedly will have a place value of 1 So this actually will represent a decimal equivalent of 2.75. On the other hand, another example is 0.101100, where the first place value is 1 half, the second place value is insignificant, the third value, which is 1/8, is 0.125, and the next place value, which is 1 over 16, is 0.0625. So we add them together, we will have a 0.6875. So that's called the fixed point representation of numbers. A fixed point number has a main drawback. By the way, the whole number part of the fixed point number is called the range. And the fractional part, which is the part after the binary point, is called the accuracy. I'm mentioning this because the main drawback of a fixed point number is it has limited accuracy. It cannot represent very small values. An alternative representation to a fixed point number is called a floating point number. The main difference is in a floating point number, the position of the binary point is not fixed. It can float according to how much quantity needs to represent. Remember before that integers cannot represent fractions, and the range of a number is limited. At the same time, the fixed point representation also has limited accuracy. So an alternative representation is called floating point. A floating point number is represented by an exponent, which represents a value to be raised to the power of 2, and a mantissa or significand, otherwise called a significand, which represent the fractional value between 0 and 1. So it's a fractional value. Consider the number 12.5. How do we convert this into floating point? We will represent this as 2 to the n times 0.006, where n represents the exponent and 0.0006 is the mantissa. N is a certain value which will raise the value 2 to an exponent. So there's a popular representation called the IEEE 754 standard to represent both 32-bit floating point and 64-bit floating point numbers. This standard is now the current standard used by modern CPUs and operating systems. So most now computers nowadays use the 64-bit and the 32-bit IEEE 754 standard. How do we convert a floating point, a number to its floating point equivalent? We just continually divide it by 2 until there will be no integer part. For example, if we convert 12.5, we first divide it by 2. So 12.5 divided by 2 becomes 6.25. We continue dividing this because the integer part is 6. It's non-zero. So we divide 6.25 by 2 again, we'll have 3.125. Since we still have 3, we divide it again. 3.125 divided by 2 becomes 1.5625. We still have a 1. We divide it by 2. We have 1.5625 divided by 2. Finally, we have 0.78125, where the whole part or the integer part is now a 0. So the non-zero part or the decimal part is used as the mantisa, and the number of divisions is used as the exponent. So we count the number of divisions. We have 1, 2, 3, 4. So 4 is the exponent, and the mantisa is 0.78125. So we represent the value by 0.78125 times 2 to the 4th, okay, which is the decimal equivalent. So that ends our video on representing number systems using decimal and binary uh, number systems. In the next video, we are going to demonstrate or elaborate on how decimal systems can be converted into binary and binary back to decimal again. Thanks for watching the video and see you in the next one.